Side 2 of the test is the part that has the particle diagrams. These particle diagrams are going to be based on 3 experiments or collections of data that we did in class. 2 of them involved a syringe, where we were putting different amounts of gas in and squeezing it to different volumes. The third one involved an Erlenmeyer flask, which we had just air in there. It didn't change size at all, but we heated it and kept track of the relationship between temperature and pressure. So I'll be referring to those. All of these particle diagrams are kind of trying to relate to, if you can imagine, one little area right inside of there, and don't draw the entire syringe or the Erlenmeyer flask. We're focusing on some mythical area, if we could, at the particle level. Suggestions is keep your particle numbers low, so it's easy to see the changes, and also just easier for you. Temperature versus pressure. What did we find out when we did temperature versus pressure? We found out the more we heated this, the higher the pressure went. And so the cooler the temperature, the lower the pressure. In other words, they're directly proportional, as long as we have it in Kelvin. And that graph looked like this graph. And so we never added more gas or less gas. So one thing that we're going to do is when we try to put a particle diagram of what happened at certain points on the graph, at point A, well, I just take 3 particles and put them in there. That means that for temperature and pressure, the constants for this were the volume of the container and the number of particles. So the constants were the volume of the container and the number of particles. So I'm going to draw 1, 2, 3 particles on every single one of those. The volume of the container, we don't really draw. We're not drawing the whole container, but it was a glass Erlenmeyer flask, so it did stay constant. We don't represent that on our diagram. We're just representing that one little square inside of that fixed volume. And then what? Now they got to be moving. Kinetic molecular theory says something about gas particles always move. They go and they perfectly bounce off each other. The temp of the gas is related to the speed of the gas. I'm going to keep these out of here for now. The temp is related to speed. So as I raise the temp from A to B to C, because it's going up on the temperature scale, that means that these need to get faster, faster, and faster. I'll make these go a slow speed. These will go a little bit faster, and these will go a little bit faster. Little whooshies that kind of represent C are going the fastest. The question is not about how fast they're going. The question is about pressure. So when I go back to the kinetic molecular theory, now I'm going to pull this back up here. I'm no longer interested in the speed. I know the speed is what it's affecting it, but when we're asked about pressure, we want to focus on these 2 F words, frequency and force. Not how fast they are, that's another F word, but frequency and force. And when they say collisions, technically the collisions are with each other, but in this case, we're talking about the walls of the container, because that's where you put a pressure sensor. We can't measure what's going on in the middle of the gases. We can just put a sensor in the side somewhere. So, on this one, I'm not going to write out a lot of words. I'm just going to tell you that since they're moving faster, they're going to collide with the walls of the container with more force. Because they're moving faster, they'll go with more force. They also, since they're going faster, those 3 are going to hit the wall more frequently. Frequently, with a higher frequency. I'll just say frequently. The 2 F words I'm going to kind of be looking for is how hard, more force and more frequency, or how frequently they hit the walls. Next one down is different. This next one's number of particles versus pressure. So this time my constants are supposed to be the temp and the volume. Once again, we don't represent the volume on here because we're not drawing the whole container. This is the one where we would put a little bit of, we'd put a puff inside of here, and then we'd always squeeze this thing back to 10. We would, no matter how much was in there, we made it fit in the perfect size, 10, well, in a chosen size, which was 10. So our mission was to keep track of what was happening to the gas. So in these ones, this time the number of particles is changing. So we need to make sure we represent that. I could put 2 of them here, 3 of them here, and 4 of them. But if you do 2, 4, 6, or 1, 3, 5, or 1, 2, 3, all of that is okay. The temp has to stay constant. So if I do this, I'm going to put a couple whooshes here, a couple whooshes. It doesn't matter how many whooshes. Maybe one would have been less writing. One way or the other, I have to be consistent. How come? Because the temp was a constant in this. Explain the difference between pressure between A and C. C has more pressure. You can just see that it's at the top than A. How come? Because even though its particles are moving and they're hitting all with the same force, I don't have to say that. I can kind of keep force out of it. They all hit the walls with the same amount of force because they're all going the same speed. But yet if I have more particles here, they're going to hit the walls with more frequency or more frequently. Because there's more particles. Not because they're going faster, not because they're hitting with more force, just because when there's more particles, they're going to hit with more frequency on the sides of the walls. And the last one. The last one is volume versus pressure. So our constants on this one were the temp, means I have to make them all the same speed. And the other constant was number of particles. This is a tricky one. This number of particles one. Because even though I declared that as a constant, I'm not going to draw the same number of particles in every box, because the box doesn't represent the whole container. The box only represents what's going inside of there. If I have a few dots here and they're all spread out, now this won't do it, but if I push them together, all those dots are going to end up over here. So that's not working very good. That's all right. And now we have one, and then if I squeeze it, I think that didn't work so well. What I'm trying to get to this idea is, however many particles we have, if we squeeze them over to this side, there's a chance that we'll have more particles inside the little box. So, even though on volume and pressure, the number of particles in that entire container is constant. The ones I draw in this little box are not going to be constant. If you squeeze them together, there will be more particles that show up. Where are they squeezed together? The lowest volume is where they're squeezed together the most. Maybe I'll put 1, 2, 3, 4, 5 of them in there. And I'm going to make a move with maybe one whooshy. As we stretch it apart, when we get to B, there's greater volume. Oh, then the particles get to spread themselves out. It's as if I'm pulling the plunger out. B is here, and C is here. This might be A, B, C. Well, C, they're going to have, or B and C have more room for the particles to go. So when I'm doing that, for B and C, I'm not going to get that many trapped into that one little area. Maybe only 3 of them moving this fast, because we said that the temperature was constant. How did we do that? Well, we didn't heat it up, we didn't cool it off. And there might only be 1 left when it comes time for, for letter C. And these numbers they don't have to be exactly the same as mine, but that works okay. So which one has more pressure on this one? This one has the most pressure. This one has the least pressure. How come? It does not have anything to do with the force that they're hitting the walls. They're all hitting the sides of the walls with the same force. The reason I know that is they're all going the same speed. And they're the same size particles. So it must just have to do with the frequency of the collision. The walls are going to get hit way more often if all those particles are in a smaller area, like A. So in this case, we have 5 particles represented. They're all squeezed in. They're going to hit the walls with more frequency. Hit the walls more frequently. That's that side of the test.